There is something deep beneath Connecticut that scientists could not clearly see before. It is not a giant crack opening beneath the state. It is not a hidden volcano. And it is not evidence that a massive earthquake is about to strike. It is something much stranger. Using earthquakes from around the world as natural sources of seismic energy, researchers have produced a new high-resolution picture of what is happening hundreds of miles beneath New England. And in that image, one structure stands out. A narrow column-shaped region beneath Connecticut appears to behave differently from the mantle around it. Seismic waves move faster through it. It extends deep into Earth's interior, and it sits right next to another enormous structure that scientists have been trying to explain for years. The discovery was published in June 2026 by researchers from Yale and other institutions in the Journal of Geophysical Research, Solid Earth. Their study provides a much clearer picture of the Northern Appalachian Anomaly, a strange region beneath New England where seismic waves travel unusually slowly. But when the researchers improved the resolution, they found something unexpected beside it, a completely different, faster structure beneath Connecticut. And that creates a much bigger question. Why would a place sitting far away from any active plate boundary contain such complicated movement deep inside the Earth? To understand why this matters, we have to go far below the Connecticut, because on the surface, there is almost nothing that looks unusual. There are forests, towns, roads, rivers, the Appalachian landscape. Nothing about the surface tells you that hundreds of miles below, Earth's mantle contains structures that are still difficult for scientists to explain. Connecticut sits in the northeastern United States, far from the dramatic plate boundaries that produce some of the world's largest earthquakes. It is not California. It is not Japan. It is not Indonesia. There is no massive oceanic plate diving beneath Connecticut today. In geological terms, eastern North America is considered a relatively stable or passive continental margin. And that is exactly why the discovery is so interesting. Scientists generally expect the upper mantle beneath a quiet part of a continent to be relatively understandable. Instead, New England has turned out to be one of the stranger places in North America when you look deep enough. For years, researchers have known about something called the Northern Appalachian Anomaly. The name sounds technical, but the basic idea is surprisingly simple. Scientists send seismic waves through the Earth, either from earthquakes that happen naturally or from other seismic signals. They measure how quickly those waves arrive at different stations. If a wave moves slower than expected, something beneath the surface may be hotter, softer, or otherwise different from the surrounding rock. If it moves faster, the material may be colder, denser, or structurally different. By collecting enormous numbers of these measurements from many directions, scientists can build something resembling a medical CT scan of the Earth. Instead of X-rays passing through a human body, seismic waves pass through the planet. And instead of producing an image of organs and bones, the technique produces a map of Earth's hidden interior. That technique is called seismic tomography. The new study used high-resolution teleseismic P-wave tomography to examine the upper mantle beneath the northeastern United States and southeastern Canada. The researchers combined data from permanent seismic networks with several dense temporary experiments, including the New England Seismic Transects, Genesis, and the Seismic Experiment for Imaging Structure beneath Connecticut, known as SEASCON. The result was a much sharper picture of something scientists already knew was there, the Northern Appalachian Anomaly. This enormous region beneath New England has unusually low seismic velocities. The new model places much of the anomaly between roughly 60 and 200 kilometers beneath the surface. That's deep enough that no drill could ever reach it. We are talking about a part of the Earth that exists far below the deepest mines and boreholes humans have ever constructed. And yet earthquakes from thousands of miles away can act like invisible flashes of light, sending waves through that hidden region. Scientists record those waves at the surface, and from tiny differences in their arrival times, they can reconstruct what is happening deep underground. The Northern Appalachian Anomaly has been puzzling scientists for years because of its location. It is enormous. It is unusually slow in seismic terms. And it exists beneath a region that is not sitting on an active plate boundary. Previous research has suggested several possible explanations. Maybe it is related to ancient hot material left behind by the movement of a hotspot. Maybe it is connected to small-scale convection in the mantle. Maybe the material is rising from deeper within the Earth. Or perhaps several processes are interacting. Scientists still do not have one definitive answer. And that uncertainty is important because the new discovery beneath Connecticut makes the picture even more complicated. When the researchers looked at the higher resolution model, they saw something very different. A narrow, nearly column-shaped region of unusually fast seismic velocities appears beneath Connecticut. It is adjacent to the slower Northern Appalachian Anomaly. And unlike the broad, diffuse structure surrounding it, this feature is relatively narrow and extends through the upper mantle and toward the base of the mantle transition zone. That is the part that caught scientists' attention. The researchers call it a fast anomaly because seismic waves travel faster through it, than through the surrounding material. But the word fast does not mean the rock itself is racing through the Earth. The movement is far too slow for that. It simply means that seismic energy travels through this particular material more quickly than expected. Think of two roads. One is filled with soft mud, the other is solid, frozen ground. A car can travel much faster over the second road. Seismic waves behave somewhat similarly. Their speed changes depending on the physical properties of the material they travel through. So when scientists see a fast anomaly, they know they are looking at material with different properties from its surroundings, but they still have to figure out what that material actually is, and that is where the story becomes fascinating. One possibility proposed by the researchers is that this structure could be a piece of continental lithosphere that has detached and is now sinking into the mantle. The lithosphere is the rigid outer layer of Earth that includes the crust and the uppermost solid mantle. Imagine a thick, heavy section of the outer shell becoming separated from the material above it. Instead of remaining attached, it could slowly sink downward into the hotter, softer mantle beneath. That process is called lithospheric foundering or delamination, depending on the exact mechanism. But the researchers are careful. They are not saying they have watched a giant slab break off and fall. They are interpreting an image created from seismic waves. The structure's shape and seismic properties are consistent with several possibilities. Another explanation is that the fast feature could represent the downward moving side of a mantle convection system. That idea takes us into something much larger, because Earth's mantle is not completely motionless. It is solid rock, but over geological time it can deform and flow extremely slowly. The temperatures and pressures deep inside Earth create enormous differences in density. A hotter material tends to become less dense and rise. Cooler or denser material can sink. Those movements can create convection. It happens far too slowly for a person to watch. You would not see the ground moving. You would not feel a giant current beneath your feet. But over millions of years, these processes can reshape continents, influence mountains, and alter the structure of the crust above. And New England may contain evidence of exactly this kind of deep movement. The surprising part is that the Northern Appalachian Anomaly itself has been interpreted by some researchers as a modern mantle upwelling or convection-related feature. Earlier studies have found evidence of unusual mantle flow beneath New England, and the region's deep structure has been linked to questions about why the Appalachians experienced unusual uplift and erosion long after the mountains originally formed. Now the new seismic model adds another piece. A slow region, a fast region, side by side, and potentially moving in opposite directions. If the interpretation is correct, scientists may be looking at a hidden circulation system deep beneath a part of North America that appears remarkably quiet from the surface, but there is an important detail we need to get right. This does not mean Connecticut is becoming volcanic. It does not mean magma is rising toward the surface. And it does not mean residents should expect a California-style earthquake disaster. The study does not make those claims. In fact, the researchers are trying to answer a much more fundamental question. How does the mantle beneath a continent behave when there is no active plate boundary nearby? That question matters far beyond Connecticut, because the Earth's continents are not simply rigid blocks floating on a completely uniform layer of rock. Their interiors contain scars from ancient collisions, old pieces of crust, buried boundaries, remnants of ancient oceans, regions that were once involved in mountain building, and structures that may have been altered hundreds of millions of years ago. Connecticut is a perfect example. The Appalachian region has an incredibly complicated geological history. Long before the United States existed, before North America looked anything like it does today, pieces of ancient continents and volcanic arcs collided along the eastern margin of what would become North America. The Appalachian Mountains formed through enormous tectonic collisions hundreds of millions of years ago. Then came another transformation. The supercontinent Pangaea began breaking apart. The Atlantic Ocean opened. The continents moved into new positions, and structures created during those ancient events were left behind, deep inside the crust and mantle. Some of those structures are still detectable today. The new Connecticut anomaly could be another piece of that ancient story, but it might also represent something that is happening much more recently in geological terms. That distinction is one of the reasons scientists need more data. And this is where the next phase of research becomes particularly interesting. Researchers are planning much denser seismic observations across Connecticut. According to current reporting on the project, Yale researchers have received funding to deploy hundreds of additional seismic sensors in the state, creating a much more detailed view of the structure beneath the surface. That matters because the better the instruments are distributed, the more accurately scientists can reconstruct the shape of the anomaly. Imagine trying to understand the shape of a mountain while looking at it through only a handful of windows. You could identify that something large exists, but you would not know every ridge and valley. Now imagine opening hundreds of windows around it. Suddenly, the structure becomes much easier to understand. That is essentially what dense seismic networks can do for Earth's interior. Every earthquake provides waves, every station records them, and when hundreds of stations are listening simultaneously, scientists can begin resolving smaller structures that were invisible in older, lower resolution models. The new study already demonstrates what this approach can reveal. The Northern Appalachian Anomaly itself becomes clearer, and the strange, fast structure beneath Connecticut emerges beside it. The next question is whether the new instruments will show that this feature is a simple vertical column, a more complicated shape, or part of a larger system extending farther than scientists currently realize. That could help distinguish between the competing explanations. If the structure looks like a detached piece of lithosphere, one interpretation becomes stronger. If it appears connected to a broader downward flow, the convection explanation becomes more interesting. And if the structure turns out to have another geometry entirely, scientists may need another explanation. That is what makes this discovery valuable. It does not close the case, it opens it. And that is often what real scientific discoveries look like. A new image does not always give scientists an answer. Sometimes it gives them a much better question. For decades, the Northern Appalachian Anomaly has been one of those questions. Why is there a large region of unusual mantle beneath New England? What created it? How long has it been there? Is it still evolving? And how does it interact with the rigid continental material above it? Now, there's another question. Why is there a narrow, fast structure directly beside it beneath Connecticut? The answers could change how scientists understand mantle dynamics beneath the entire eastern United States. And there is one more reason this matters. The Earth's surface is where we live, but the forces that shape it often begin much deeper. Mountains can rise because of processes occurring far below them. Continents can change shape because of forces generated inside the planet. Old geological structures can continue influencing the surface long after the plate boundary that created them has disappeared. Even regions that appear tectonically quiet can contain an incredibly active geological history underneath. Connecticut is not suddenly becoming a dangerous volcanic zone, but it may be revealing something much more interesting. The Earth beneath North America is more complicated than the surface makes it look, and scientists are only now getting the resolution needed to see some of that hidden architecture. The biggest takeaway from this discovery is therefore not fear, it is scale. When you stand in Connecticut and look across the landscape, everything seems permanent. The mountains seem fixed, the ground seems solid, the continent seems immovable, but hundreds of miles below, rock can slowly deform and circulate. Ancient pieces of Earth's crust can separate from the material above them. Hot and cold regions can coexist. And structures that began forming millions or even hundreds of millions of years ago can still be visible in the seismic fingerprints recorded today. That is what makes the new Connecticut discovery so compelling. Scientists did not suddenly discover that the Earth beneath Connecticut is breaking apart. They discovered that the deep structure is far more complicated than a simple, quiet continental interior. And the more clearly they look, the more questions appear. The new seismic model has given researchers a sharper picture of the Northern Appalachian Anomaly and revealed the unexpected fast anomaly beside it. The leading explanations include a detached piece of continental lithosphere sinking into the mantle or a downward flowing part of a convection system. But neither explanation has been proven. That distinction is important, because this is not a prediction of an impending disaster. It is something more fundamental. Scientists are discovering that the planet beneath our feet is still full of structures we do not completely understand. And Connecticut may now be one of the best places in North America to study that hidden world. The next generation of seismic measurements could reveal whether this strange structure is an isolated fragment, part of a much larger mantle circulation system, or evidence of a process scientists have not yet fully recognized. And if the answer turns out to be different from what researchers currently expect, that would be the most interesting outcome of all. Because every improvement in our ability to see inside Earth has produced surprises. We once imagined the planet as a series of simple layers. Now we know the reality is far more complicated. The mantle contains rising regions, sinking regions, ancient scars, chemical variations, temperature differences, and structures that can extend hundreds of kilometers through the planet. And sometimes the evidence is hiding directly beneath places where millions of people live, work, and go about their daily lives without ever realizing what is below them. Connecticut is simply the latest reminder. The ground beneath you may look still, but deep inside Earth, nothing is truly simple. And if you want to understand the strange changes scientists are discovering beneath our planet before they become widely known, subscribe to WideView. We will keep following this story as the new seismic measurements come in, and scientists learn whether this hidden structure is a relic of Earth's ancient past or evidence of a deeper process that is still happening today. Because the most fascinating part of this discovery is not that scientists found something beneath Connecticut, it is that they finally developed a clearer way to see it, and now they have to figure out what they're looking at.